Hello and welcome everyone to the Varsity Tutors StarCourse series, where we're curious about chemistry largely because chemistry is pretty magical. And that's why we've brought our friends from Pacific Science Center. You see Holly Duskin here on the screen. They're going to show us the colorful world of chemistry as we investigate what kinds of chemical reactions give us bright, vivid colors, really cool looking textures, and some other pretty cool surprises along the way. I almost said supplies because I have a couple announcements for you guys before I turn it over to Holly. One, on the page where you registered and coming up here in a second, Holly's got some supplies. You will be able to participate in one of today's experiments and be able to report some of your results to us. So if you've got some of those household items laying around, grab them. If you prepare them in advance, have them nearby. If you don't, that's okay. This is being recorded. You can always come back and do them later, or there's plenty to enjoy by watching Holly demonstrate all these things as well. Also, make sure you use the chat box to the right of the screen. Holly's going to be asking you questions throughout to find out your observations and predictions about a lot of these reactions. And so we want to hear from you. Use the chat box for that. And if you have any questions throughout today's show, use that chat box to ask them. In the last 10 minutes or so, I'll interview Holly with your questions, and we can get some deeper answers about what's going on in the world of colorful chemistry. Last thing for you, have a camera nearby because we're going to take a picture. We'll have a couple of options for you guys to lean into the screen, get a selfie with your experiment results, and some other cool things Holly's going to show off. We'll do that in about 35 minutes. If you do that and upload to Instagram, tag PacSci and Varsity Tutors, you'll be entered to win a spot in Curious World Club. And I know we've got some of the Curious World Club kids here in our live studio audience hanging on for a bonus Q&A session at the end of class. I'll give you guys your instructions for that when we get there. With all that said, it's time to turn it over to your teacher for today, Holly from Pacific Science Center.
Thank you so much for the warm welcome, Brian. And hello, everybody. Again, my name is Holly. I am joining from Pacific Science Center today. We are a super cool science museum over here in Seattle, Washington, but I am so excited to be here with all of you all over the country and across the world. So thanks so much for joining us. Just like Brian said, our program today is all about chemistry. And I really like the study of chemistry because it's really just all about all the different stuff that is in the world around us. So soft stuff like maybe a t-shirt, hard stuff like maybe a countertop, maybe even some liquidy stuff that sloshes around, and even invisible stuff that is in the air all around us. Now, I've been saying stuff a lot, and scientists actually have a special word for all of this stuff. They call it matter. So I'm made of matter. You are made of matter. All that stuff that we just pointed to is made of matter. So what I want you to do right now, scientists, is point to some matter near you. What is something that's made of matter? Go ahead and find something. Okay. Point to something else with matter. All right. How much more things made of matter can you find? Go. All right, I hope all of you just invented some super cool dance moves, but that's right. Everything around us is made of matter. And today in our program, we are going to be finding out what happens when one type of matter meets and interacts with another type of matter. Now, we call that a reaction. Now, you might notice I have a lot of neat stuff up here on stage with me. We are going to be doing some super cool reactions together, but some of it is a little bit dangerous. So before we get going with our reactions, I do want to invite all of you to say our safety oath with me. So go ahead and put your favorite hand in the air. Wave it around like you just don't care. All right, and then go ahead and repeat after me. I state your name. Promise to never, ever, play with fire or chemicals. Because I like my face and all my stuff just the way they are. All right, thank you so much, scientists. Go ahead and put those hands down. I think we are ready to go ahead and get started with our first demonstration here. Now, luckily here at the Science Center, we are specially trained to do these demonstrations. So I'm going to get us going here with our first one. And your job as great chemist, just like all scientists, is to make some observations. See what you notice happening here, and then get ready to share with me in the chat some of the things that you observe. I could also use your help giving me a great big 3, 2, 1 countdown. So go ahead and get those hands out. Here we go. In 3, 2, and 1. All right, chemists, let me know in the chat, what did you see or observe there? Ooh, I'm seeing some great comments coming in. A lot of folks are saying fire, flames, fire explosion, a little bit of smoke. Someone's saying I kind of blew air into that tube. Some fire came out of the top of the can. Some really excited folks. That's right. I saw that fire as well, but I have a question for you, scientists. Do you think that fire that we just saw, was that a chemical reaction? Can maybe let me know in the chat. Yes, you think it was a chemical reaction. No, not so much. Maybe you're not so sure. All right. Okay. We got some good guesses coming in. A lot of folks are thinking maybe yes. This is a little tricky. Well, we were seeing a chemical reaction. It was actually a special chemical reaction that we call combustion. So combustion is just a chemical reaction that results in fire, just like the fire that we just saw. And I'm hoping all of you can help me figure out what 3 ingredients belong on this triangle. These are the 3 things that we need in order to make a combustion or fire reaction. So to get us started, the first one had something to do with that air I had to blow into the tube. If you think you might know what that first ingredient is, go ahead and let me know in the chat. All right. Yeah, I see some people are saying air. Exactly. It's something in the air. Something that not only combustions needs, also humans need this thing in the air. We need it to survive. All right, nice job. Looks like a lot of folks are getting it. Our first ingredient is oxygen. All right, for our next 2 ingredients for combustion, I want you to think about if you were maybe going to go on a camping trip, you wanted to make a big campfire to help you stay nice and warm. What kinds of things would you bring with you to make that fire and get that fire going? Let me know in the chat. What would you bring with you to make that fire? All right. Okay. I'm seeing a lot of ideas. People are thinking, ooh, some things like some wood or some logs, maybe some newspaper or other things they could burn. Absolutely. Okay. So those are going to be examples of our next item. Fuel. A fuel is anything that can burn, like a lot of those objects that you were just mentioning. Now, the fuel that I was using inside of our tub there at our beginning demonstration, that was a special kind of fuel called lycopodium powder. It is super flammable. It actually comes from some moss spores that are dried up. Very cool. All right, let's see. What else are folks saying in the chat? Some people are saying not only would they bring wood, they might also bring things like a lighter or maybe matches, or somebody was even mentioning like some flint or some stones or rocks. That would be super cool if you could use that to start a fire. I am not quite so talented, but all of those things are examples of our third ingredient, heat. So we're going to need some kind of heat source to get our combustion going. All right. Hey, nice job, scientists. We know that we need oxygen, fuel, and heat to get a combustion reaction, which is just that special type of chemical reaction. So I think we're ready to do another demonstration. Let's see what would happen this time. Now, for my fuel, I actually have a whole jar of that really special lycopodium powder that I mentioned. Remember, it is super, super flammable. So I'm kind of curious what would happen if we just took a lit match and put it right into this whole jar. So maybe make a prediction and actually let me know in the chat, what do you think is going to happen when I put a lit match right here into our fuel jar? We're going to find out together. You can give me that countdown again. Some people are guessing it will explode. There will be a big boom. All right, here we go. 3, 2, and 1. Was that what you expected, scientists? Was not exactly what I would have predicted. It does not exactly line up with a lot of the predictions I'm seeing in the chat. So I'm curious where we went wrong. Why did we not get a combustion reaction this time? Well, looking at our triangle here, let's see. Fuel, did we have fuel? Yep, we got a whole jar here. And how about heat? We have that. Yeah, we had our lit match. It was giving off some heat here. I see a couple scientists already guessing in the chat. Yeah, no oxygen. That must have been what we were missing. Well, I think we can actually test this out with a little experiment here. Let's try to light this lycopodium powder on fire again. But this time, instead of keeping it in the jar, I'm actually going to put a little bit of it right here onto my hand. And we're going to use our matches again as our heat source. But this time, I'm going to be throwing this up into the air so that we mix in a whole bunch of extra oxygen. And let's just see what happens. See if maybe that helps us out. So go ahead and get ready to give me that countdown again. Here we go, scientists, in 3, 2, and 1. All right, what do you think? Do you think we got a chemical reaction this time? Let me know, yes, no, maybe. All right, I'm seeing a lot of folks saying, yes, chemical reaction. We saw that fire, that sign of combustion. So I'm gonna do our fire throw one more time, but this time I would like you to be thinking about what do you think is happening to this lycopodium powder during our combustion reaction? So try to watch the powder, just think about that and be ready to share your ideas with me in the chat. What is happening to our powder during this reaction? Here we go, one more time, 3, 2, 1. All right, I'm gonna check out our chat, see what our scientists are thinking here. Ooh, I like that word. Someone said it's being oxygenated. Yeah, so something having to do with all that oxygen in the air is helping that lycopodium powder to catch on fire. And you're right, we did find out that our lycopodium powder here in our jar, because it's all packed so closely together, there wasn't enough oxygen to get our full reaction. All right, yeah, so people are thinking, maybe it burned up, it kind of disappeared, it went into the air. Yeah, I'm not seeing it on the floor or the ceiling. So yeah, something definitely happened to that lycopodium powder. So would you believe that powder on my hand during that reaction, it actually transformed. It changed into something else. It changed into an invisible gas called carbon dioxide. Has anybody heard of carbon dioxide before? Does that sound a little familiar? Yeah, you might recognize this as the same gas that we exhale when we breathe out, one of the gases in our atmosphere. But how does lycopodium powder turn into the invisible gas carbon dioxide? That just seems totally silly. Well, scientists, it all has to do with that matter that we talked about at the beginning. You see, matter is made up of some really teeny tiny particles called atoms. Now, atoms are so small. We can do a little demonstration to show us how small they are. I want you to find a strand of hair. Maybe it's a strand of hair on your head. Maybe it's a strand of hair on your arm. Maybe you've got a cat or dog hair stuck to your sweatshirt somewhere that you could take a look at. Now, looking carefully from one side of this tiny thin little hair to the other side is 1,000,000 atoms across. That is just how small these atoms are. Now, these atoms, they don't actually like to just hang out by themselves. They're so tiny. They actually like to bond together with other atoms. And when they do that, we call them molecules. Now, I kind of like to think about it like this. Our atoms are kind of like letters, right? They're small, they're hanging out by themselves. But when we put our letters together, they form a word, just like how our tiny atoms can bond together to form molecules. Now, the really cool thing about chemical reactions is that we can have a couple different types of molecules. Maybe we got molecule green, we've got molecule leaf, made up of all these little letters here, or atoms. During a chemical reaction, those atoms are going to get all jumbled up and they are going to form new molecules, form new words. And that's how something can transform into something else. So let's all say 3, 2, 1, react together and see what happens to our molecules here. Ready? 3, 2, 1, react. All right, here we are at the end of our reaction. We've got some new molecules, molecule eagle and molecule fern, but they're made up of those same original letters, those same atoms. All right, my scientists, I think that we might be ready for another demonstration here. Now, for this demonstration, I am going to need a very special object. I'm curious if maybe you can help me guess what it is. This special object is a greenish color. It is a rectangular shape. It's kind of papery feeling. If you think you might guess what it is, go ahead and tell me in the chat. I'll give you one last clue. There's a picture of a dead president on this special item. Ooh, good guesses. People are thinking leaf and money, dollar bill. Exactly. That is our next ingredient that we are going to need here. Now, I actually asked Brian from Varsity Tutors to mail me one of his hard-earned dollar bills so that we could light it on fire today. Ooh, Brian, are you still out there? Okay. I think, uh-oh.
I'm
okay,
just
Brian is
crying. I worked hard for that.
He's still here. Okay. We're going to be super careful with your dollar, Brian. Don't you worry. But we are going to do a little experiment with it. So I have with me some special fuel here. It's called isopropyl alcohol. And we're going to see what happens when we take Brian's dollar bill. We dunk it into our special fuel here, and we add it to our heat source, right? So we got fuel, we got heat. There's plenty of oxygen in the air all around. I see some people making some predictions already in the chat about what they think is going to happen here. So yeah, go ahead and let me know if you've got a guess. Hopefully Brian doesn't read those comments too closely. He might get a little scared. All right, scientists, go ahead and get me the 3, 2, 1 countdown again. So here we go. In 3, 2, and 1. Here we go. Oh my goodness. All right. That was a little different than what some of us predicted. I saw some predictions were saying it might go boom, it might burn up. Well, let's try that one more time just to be sure here. If you've got a thought about maybe what's happening here, you can, of course, let me know that in the chat as well. If you have a guess about why our dollar bill is not burning up the way we thought. Let's try this again in 3, 2, and 1. Here we go. Here goes Brian's dollar. Just fizzled out again. Well, I have a question for you, scientists. Do you think that we got a chemical reaction? You let me know yes, no, maybe in the chat. And if you're thinking maybe, think about this though. Did we see fire? Did we see some fire on this dollar bill? Yeah, I did see a bunch of flames going all over our dollar. So if we saw flames, that means we saw combustion, which means we saw a chemical reaction, but it didn't actually burn up the whole dollar. And that's because it turns out fire can actually burn at different temperatures. So our isopropyl alcohol fuel here only has to be about 250 to 300 degrees Fahrenheit in order for it to burn. But paper actually has to be a lot hotter. It has to be 451 degrees Fahrenheit before it will burn. If anybody's heard of that book, Fahrenheit 451, that's what it's referencing, the temperature it takes for paper to burn. Now, we have a special word for this. We call it activation energy. So some fuels have a lower activation energy. It's easier for them to catch on fire at a lower temperature. Other objects have a higher activation energy. It takes a lot more in order for that object to actually be able to burn. All right, Brian. It looks like you are in the clear. We did not actually burn up your dollar bill, so I'll keep it super safe for you and mail it back.
Thank you very much. I love science now. I was skeptical, but I love it again.
All right, my scientists. Well, we've seen some cool chemical reactions so far, but how do we actually know when we are seeing a chemical reaction or not? So there's actually 4 different signs or kind of clues that we can look for to help tell us if we're seeing a chemical reaction. So we're going to go through those 4 signs, and then we're going to do some more demonstrations and see if we can find those signs. So our first sign is heat. If we notice something getting hot or warming up, that is a sign of a chemical reaction happening. So go ahead and let me know in the chat, what are some things that you can think of that get hot, get warm, or give off heat? Maybe even look around in the room around you, see if you can see some things, maybe think of some things outside. All right, so folks are thinking of lots of different things. I see an oven, a stove, the sun, a lamp, a heater. Someone says their cat. Love that. And even what about ourselves? Our own bodies are giving off heat as well. So it turns out there's actually chemical reactions happening inside of our body to help us stay warm. So those were all some great examples of some chemical reactions giving off heat. All right, our next clue is gas. Now, this one is a little bit tricky because, as we mentioned earlier, that gas is oftentimes invisible. So since we can't see it with our eyes, sometimes we have to observe it with our nose. Sometimes it gives off an odor or a smell that we might be able to detect, or we can even look for something bubbling. So bubbles are just gas that is trapped inside of something. So that's another sign we can look for. All right. Our third clue is light. So if you see something glowing, giving off light, go ahead, let me know in the chat some examples, because that could be another sign that whatever that thing is giving off light probably has a chemical reaction going on that's causing that light. Ooh, some wonderful ideas coming in. Folks are thinking of things like glow sticks, the sun again. So some of those things that gave off heat also give off light. So seems like some of these things can have more than one of these 4 signs. Love that. All right, light bulb, computer. Yeah, some of our electronics might be giving off light as well, electricity. All right, nice job. And my 4th and favorite sign of a chemical reaction is color change. So if you notice something changing color from green to orange, red to yellow, white to clear, right? Anything like that, that could be another sign of our chemical reaction. I always like to think of things like even color changing nail polish, for example. There's actually some chemical reactions happening there to cause that color change. People are thinking of, glow sticks again. When those chemicals inside mix, they cause that chemical reaction. All right, my scientists, now that we know about these 4 signs, so heat, gas, light, and color change, we're going to do another demonstration and see if we can maybe find some of those clues happening. So for this demonstration, I have 3 different fuel sources that we are going to be testing out. My first fuel source is actually isopropyl alcohol again. So that same thing that we used for our dollar bill experiment. And we're going to see what happens when we add this fuel source to our heat here. So get ready to be telling me in the chat if you notice any of those 4 signs happening. Let's see which ones we might find here. All right, my friends, go ahead and get out those 3s ready to give me that countdown. And here we go in 3, 2, and 1. Ooh, that was interesting. All right, what did you notice happening? And did you see any of those 4 signs? Yeah, someone's letting me know in the chat. They saw fire again. Absolutely. Heat. Yeah, probably was hard for you to feel it, but I can tell you, I definitely felt some heat coming off of that reaction. People noticed light, exactly. And I kind of noticed an orangish yellow color to that light that we just saw from our isopropyl alcohol. Awesome. People are also mentioning an explosion. It got bigger. There was a lot of it. It kind of put out my candle here. Yeah, maybe I was squeezing a little bit too hard there. All right, scientists, I think we're ready for our second fuel. So our next one is called copper sulfate, actually a type of metal that I have mixed in here. So let's watch and see if we can notice any differences from our regular isopropyl alcohol to our liquid that has that metal copper mixed in with it. All right, here we go in 3, 2, and 1. Oh, interesting. All right, what did you see happening? What was different about this fuel source? Folks are saying color change. There was a different light. A lot of people are sharing the color green. I saw that as well. So it turns out when this metal copper goes through this chemical reaction, goes through some combustion, it gives off a green color. A green explosion. I love that. All right, scientists, I have one more fuel for us to test out here. This one is called strontium chloride. It's actually a type of salt. So let's see what happens with this one and watch closely to see if you might notice something different than our other two that we have already seen. All right, here we go. 3, 2, 1. Ooh. What did you notice about that one? All right. Yeah, people are noticing they saw light again, heat again, more of those signs of a chemical reaction. Some folks are using some describing words like red or pink, right? Exactly. I think it kind of looks like a bright pink magenta color. So it turns out our strontium chloride salt does turn a little bit pinkish red when it goes through combustion. Our copper turns green. So these different ingredients, different types of metals or salts, different fuels, they show us different colors when they go through that reaction. And we can actually use ingredients like these in fireworks. So if you've ever seen a pink or green firework before, you might have seen this metal or salt before. We put those things in our firework, they go up in the sky, and when they have that combustion reaction, we get to see those different colors. I am kind of curious what might happen if we mix together our pink and our green. Do y'all want to see it? Okay, let's test it out. We're going to do one more here. So give me that 3, 2, 1 again. In 3, 2, and 1. Whoa. All right, scientists. That was super fun. We saw a bunch of different signs of those chemical reactions happening. Ooh, man, I am just feeling really tired up here doing all of these experiments. And I hope y'all don't mind. I might just take a quick water break if that's okay with all of you. I got my super big water bottle here. I just like to stay hydrated when I'm doing science. And I don't know about you all, I actually really like bubbly water. Does anybody like LaCroix or Soleil? So I just like to get my water all nice and bubbly before I take a really nice big sip. What is happening to my water bottle? If you are noticing something strange, let me go ahead and let me know in the chat. Some folks are shouting at me in the chat, color change. Yes, I am seeing that too. It looks like my water bottle has turned blue. And I agree, we are seeing color change from clear to blue. That is a sign of a chemical reaction. So I'm thinking there might not have just been water inside of this water bottle. And that's right. I actually had a special ingredient in here called methyl blue. It's what scientists call an indicator, and it's going to change to the color blue when it interacts with oxygen. So when I shook up my water bottle, I brought all of this extra oxygen from the top down into my liquid. It met up with that blue indicator, and it showed us our color change from the chemical reaction that was going on. So I don't think I'm going to drink this. Should I still drink this? Okay, no, I'm not going to listen to the people saying yes. I am going to set this aside. I am not going to drink this water bottle right now. But I do have something else cool for us to check out that also uses that indicator ingredient that we just talked about. This one's a different indicator though. It's called universal indicator. It's the green color that you see inside of this tube here. And what we're going to do is on one side of our tube over here, we're going to add a special type of matter called an acid. And on the other side, we're going to add a special type of matter called a base. So while I'm getting ready to add this, I would love to hear from you all. Do you know any examples of some acids? Maybe you already know of some. If you want a hint for some acids, a lot of times they are things that might taste sour. So go ahead and let me know your thoughts in the chat. What might be some examples of an acid? Ooh, I love these ideas. Okay, a lot of people are going with the sour theme. So they're thinking of things like warheads or lemons or limes, orange juice, grapefruit. Yep, exactly. Citric acid, which you might have seen as like an additive in some different foods. Limes, exactly. And somebody mentioned something really interesting, an acid that's actually inside of us. Everybody point to your stomachs. We have stomach acid inside of us that's helping us to digest our food. Now, the acid that I'm going to use is called hydrochloric acid. It is a super, super strong acid, so I am just going to use a tiny little bit here. All right, now on the opposite side, we're going to put that base. So go ahead, think for a minute, share with me in the chat if you can think of some examples of a base. Now, if you need a hint, you might want to think about sometimes there are some different household cleaning items that are bases. They sometimes feel kind of slippery. So let me know if anything's coming to mind for you there. All right. Yeah. So it looks like some folks are thinking of some different types of bases here. Someone mentioned baking soda. Yes, used for cleaning. We also use it for baking. That is an example of a base. Some people are mentioning things like soap and bleach. And yeah, things like even dishwasher soap. Those are all going to be examples of those bases, things that are really slippery. Mr. Clean. I love that. All right, so the base I'm using again is a super strong one, so I'm just gonna add a couple little drops here. And then we're gonna take a closer look at our tube and see what we notice. So I would love for, again, all of you to get those scientist observation eyes on and keep a close lookout, especially for any of those 4 signs that we talked about earlier. So let's see what's happening inside of our tube. All right, go ahead and start sharing with me in the chat. What are your observations? What do you notice happening? Ooh, a lot of folks are noticing one of those 4 clues in particular, color change. Exactly. So that might be a sign to us that we do indeed have a chemical reaction going on inside here. Ooh, somebody's noticing it's turning red on one side and kind of a bluish black or maybe purple on the other side. Great observation. Somebody was noticing it's still green in the middle, right? Where that green universal indicator started out. We do call this demonstration rainbow tube. You can probably see why. But yeah, this side over here where it's a little bit bluish color is where we added that base. So when our green universal indicator mixes with a base, it turns to a dark blue. And on this side of our tube is where we put that acid. So when our green universal indicator mixes with an acid, it turns to that reddish color. Now, as it's slowly getting mixed up, some other scientists were mentioning to me they saw this clear part or this air bubble. So I left a little air bubble in the end just to help us kind of mix up and stir those things together to make sure our matter interacted with each other and started that chemical reaction. But as it's slowly mixing together, that red and that blue are working their way towards the center. Awesome job. All right, my scientists. Well, great observations with our rainbow tube here. I think we are just about ready for one of our last demonstrations here. Huh. Now, wait a second. I'm noticing something a little bit strange happening. Does anybody see anything a little bit odd up here on one of my tables? Can any spot something strange? Yeah, a lot of people are saying the water is clear again. What is going on? Here's my water bottle. Do you think should I shake it again? Should I shake it again and see what happens? Okay, let's shake it one more time. Ooh, okay, it's turned back to blue. This is very mysterious indeed, chemists. What is going on? Well, here's the thing. A lot of chemical reactions are non-reversible, which means once all that material gets used up, it's all gone, right? Think about those combustion reactions earlier. Once we burned up those fuels, we couldn't really unburn them again, right? But there is a few special reactions that are reversible. They can kind of keep going backwards and forwards over time. So this is kind of like that. What was going on is that I had a couple other special ingredients inside of this water bottle here, and I had two other ingredients that were inside the water that were using up all of that oxygen. They were taking the oxygen away, and that's when our methyl blue turned clear. It didn't have any more oxygen for it to react with. But when we shook it up again, we added that oxygen back in, brought our oxygen back into contact with that methyl blue indicator, causing it to turn blue once more. So I'm going to set this aside. We're going to let our other special ingredients do their work, take the oxygen out, and we can watch again to see if it turns clear one more time. We'll see what happens. All right, friends. So as I mentioned, we got one more really cool demo before we do that hands-on experiment. Now, for this last demonstration, we have seen some super cool color change, right? We have seen a lot of heat. We have seen a lot of light. But what was that fourth sign? If you remember it, let me know in the chat. I don't think we've seen much of that one yet. All right. Yep. Some folks are guessing it. It is gas. That was that fourth sign. We haven't really gotten a chance to see that much. So for our last demo here, I've got a few things to help us out to see if maybe we can get a chemical reaction that gives off gas. Now, our main ingredient for this is going to be something called hydrogen peroxide. You might recognize this bottle. Some folks have this in their homes to help them kind of clean out cuts and scrapes. But you'll always notice it's going to be in a really dark colored bottle. And the reason why it's in this dark colored bottle is to protect it from the light. Because as soon as our hydrogen peroxide meets the light, it's going to start a chemical reaction. Now, our hydrogen peroxide is also called H2O2 because it is made up of hydrogen atoms and oxygen atoms. And when it meets with the light, it's actually going to change, just like we talked about earlier about how those atoms get all mixed up. They're going to get mixed up and they're going to change into H2O. If you know what H2O is, you can let me know in the chat. And O2, which that O2 is going to be oxygen. So it's going to give off oxygen gas into the air. And I see a lot of folks shouting in the chat, it's water. That's what the H2O is exactly. So that's the liquid that is going to be left behind. So let's go ahead, open up this hydrogen peroxide. I'm going to pour some into my graduated cylinder. And let's see what happens when it meets the light. All right. Look closely. Let me know if you see any of those four signs happening. What do y'all think? Chemical reaction? Yes? No? Maybe? Don't feel any heat. I don't see any light. There's definitely no color change. It's just clear. Oh, you know what? Oxygen is invisible, folks. Even if it was giving off oxygen, we wouldn't be able to see it. How are we supposed to know if it's giving off gas or not? Well, we're definitely going to need to fix this. I'm going to put our hydrogen peroxide into a bigger graduated cylinder here. We're going to need to add another ingredient to help us see that oxygen gas. And I'll bet all of you might actually be experts in just how to do this. Has anybody here ever blown bubbles before? Yeah. Okay. We got a few bubble blowing experts here. Well, think about this, folks. When you get that bubble wand, you dip it in some soap and you blow into it. Now you've got a bubble floating around and it's holding all of that gas from your breath that's now trapped in that bubble, and we can kind of see it. We can kind of see that gas floating around. So luckily, I've got some handy dandy soap here, some dish soap. We're going to add this and see what happens. All right, go ahead and give me that countdown, scientists. 3, 2, and 1. All right. Huh. What do y'all think? Chemical reaction? Yes? No? Maybe? We'll give a little stir. You know, I am seeing some blue, but it's like that's just the color of our dish soap. So no color change, no heat, no light. I'm not even seeing any gas bubbles. Well, turns out there's one more thing I didn't tell you yet about this chemical reaction, scientists. And that is that this chemical reaction is actually going very, very slowly. So some chemical reactions, they go super quick, right? Just like those demonstrations that we saw earlier with our combustion. But other chemical reactions happen quite slowly. You might even think about some rust, right? That's an example of a chemical reaction. Has anybody seen rust before, like maybe on an old nail or an old bike, right? When it gets some water on it left out in the air. But how long does it take something to get rusty? Yeah, it can take like months and months for that thing to get rusty, for that chemical reaction to happen. Yeah, some folks are saying it takes a really long time. I agree. Now, we don't really have months to wait unless, do y'all have the time? Should we just watch it and see what happens? No? Okay. Okay. People are saying no. They don't have months to wait. So luckily for us, we do have one last special ingredient. So chemists can sometimes use something to actually speed up a reaction and make it go faster. We call those things a catalyst. Now, there's lots of different types of catalysts. The one I'm using is called sodium iodide. It's a type of salt. And again, like I said, what it's going to do is just keep our reaction the way it is, but just speed it up, make it go a little bit faster. So here we go with our final ingredient. Let's see what happens, scientists. Give me that countdown. 3, 2, and 1. Here we go. Oh my goodness. Did we get a chemical reaction? What do you all think? Yes, I agree. Well, what are some things that you're noticing or seeing? How can you tell that we finally got a chemical reaction? Let me know in the chat what your observations are and if you saw any of those 4 signs. I do see some scientists telling me elephant toothpaste. Yeah. This demonstration is called elephant toothpaste. That's one of the names for it. Some people are commenting it was an explosion. It blew up. I see a lot of people using the word foam or foamy. Yeah, so all of this foam that is here is really just those tiny bubbles filled with gas. So this is how we were able to see that oxygen gas. It got trapped inside of our soap and it turned into all of this foam. Now, somebody else was mentioning heat. So this one was a tricky one to see, but you might have noticed at the very beginning a little bit of vapor coming up. So if I put my hands really close I can actually still feel some heat coming off of this. So we call this an exothermic reaction. That means one that gives off that heat sign that we were talking about. Now, scientists, I'm going to show us a slow motion video of our elephant toothpaste happening again, but this is going to be your opportunity to get that selfie shot. So remember, if you take your photo, you post it to social media, you tag Varsity Tutors, you tag PacSci, you will be entered to win our prize. Now, I'm going to show us that video again. Go ahead and get those phones or cameras ready. Don't worry, it starts off a little bit slow so you can watch the beginning. But remember, you know what's coming, friends. So I hope you've got those cameras ready. You're ready to take that photo when you think the moment is right. Maybe you want it about now with our foam shooting up in the air. Maybe you want your selfie now when you can see all of that foam piling up. I'm even noticing a little bit of that steam coming off of our elephant toothpaste, that exothermic reaction, that heat is showing up for us here. Go ahead and get that photo, folks. Now, I noticed some other people were mentioning a little bit of color change too. I'm seeing that as well, a little bit of yellowish color. And that's going to be due to our catalyst. Our sodium iodide does have a little bit of a yellowish color to it, as you probably noticed, showing up there. All right, my scientists, hopefully you've gotten your awesome shot, your selfie shot with our elephant toothpaste here. So I've got mine here. It's kind of collapsing down. Some folks were noticing in the chat too, it was kind of shrinking or disappearing. But that's what's happening, right? Our bubbles are kind of popping over time and releasing that oxygen gas into our atmosphere. So that is why our foam is kind of shrinking down a little bit. All right, my friends, we are moving on to our very last activity of our program today, which is when you are going to need some of these optional materials if you would like to. So we're going to set ourselves up to do a little bit of a chemical reaction of our very own. So if you would like to participate, take this moment to go ahead and grab those materials. That plate or tray that is mentioned is something that you'll want to put underneath just to catch any spills. So it could be something like a baking sheet or just a plate, something like that. Somebody was asking me earlier about what kind of vinegar you need. I'm going to be using just regular white vinegar, but if you have a different type of vinegar, you can definitely try that out. I don't see why not. All right, so hopefully you've had a chance to gather those materials. I've got mine right up here on stage. And we're going to go ahead and start with our zip top bag. So you're going to need just one to get going. Remember, if you've got your materials, you can just follow along with me at home. If you don't have materials, that's totally fine. You can just watch and observe up here on stage. And of course, feel free to share your observations or thoughts with me in the chat. Now we're going to start with our zip top, like I mentioned. And I've got that tray right underneath me here. So right from the get-go, I want to make sure to keep this here just to protect me from any possible spills. Next up, we are going to add our vinegar. So this is going to be one of our ingredients today. Let's go ahead and let you know how much you are going to need. So we're going to use half a cup of vinegar. Hopefully you've got a measuring cup of some sort. Maybe it's nice and big like this. Maybe you've got some small measuring cups. I'm going to measure out my half cup. All righty, here we go. And next, I'm going to pour my half a cup of vinegar right here into my zip top bag. Now, you do want to be a little careful not to spill. This is a really safe demonstration for you to do at home, but we just don't want it to get too messy. I'm going to prop my bag up like this so it doesn't fall over. See if I can get that a little easier to see. All right, we good so far? Y'all got that? Okay. Next, I'm going to give you a little closer up look here. of our experiment, we are going to use that tissue. Now, if you don't have an actual tissue like a Kleenex, I'm just using half of a napkin here. You could also use maybe some paper towel squares or some tissue paper if you've got it. And I'm going to add 1 tablespoon of my baking soda right here to my tissue. I'm going to try to put it right here in the middle. Okay, got my scoop, putting it in the middle. Hopefully y'all are following along at home with me. All right, next I'm going to take my tissue here and I'm actually going to very carefully wrap it up. I'm going to keep that baking soda right down in the middle. I'm going to give it a little twist to keep that baking soda nice and safe inside. I'm going to set that aside for just a moment. I'm going to get my bag ready to go. So I'm going to tell you what we're going to do first so you can make a prediction. We are going to take our baking soda and tissue. We're going to drop it inside of our bag and we're going to super quickly seal it shut. Then we're going to see what happens. So maybe make a prediction right now before we do it. Do you think we might see any of those 4 signs of a chemical reaction? Something kind of interesting to note about this is that our baking soda was one of those bases that we mentioned earlier, and our vinegar in here is one of those acids that we talked about. So they're kind of like opposite types of matter here. All right, I think we are about ready to make our experiment happen. I am going to zip my top about halfway closed so that it's a little easier for me to close it super fast. Speed is going to be key here, folks. I'm ready to drop this in, seal it shut, and then we're going to watch and see what happens. I did want to give one last warning. If you are doing this in the place that you are learning right now, if you don't like loud noises, that might just be something to be aware of. There could possibly be a little bit of a loud noise, so just be prepared for that if that's something that bothers you. All right, are you ready? Go ahead and give me one last countdown, scientists. 3, 2, and 1. I'm dropping it in. I'm sealing it up super quick. Let's watch carefully and let me know what you see happening. I'm going to give it a little bit of a shake. Oh boy. Oh goodness. Uh-oh. I see a lot of great observations. People are noticing lots of bubbles, lots of fizzing. It looks like my bag has a little bit of a hole. People are noticing it's getting more foamed up. There's a whole bunch of air getting trapped inside of our bag. Look at that. I'm lucky my bag did not pop. It didn't make a super loud noise, but I wonder if any of yours did. You can let me know in the chat if you got a loud pop from yours. All right, I'm going to go ahead and open my top. Oh, there goes the pop. All right, scientists, so let me know. Do you think we saw any of those 4 signs of a chemical reaction? I'm not feeling any heat from mine. Let me know if you feel any from yours. Ooh, yeah, I'm seeing a lot of folks saying gas in the chat. Exactly. So using that soap and those bubbles that we used earlier, that was one way for us to capture gas and to be able to see it a little bit better. But this was another way for us to trap that gas inside of our Ziploc bag. And then we were able to see that invisible gas by noticing our bag getting more and more full. Great job. If you were able to do this demonstration at home, you can let me know in the chat what your results are. And I did just want to share with you that this really was kind of a demonstration. It was just showing us what happens when we mix these things together. But you can really easily turn this into more of a true experiment. And the way that we make it into an experiment is by changing one of the variables and then doing our demonstration again. So if you have an idea of one of the variables you might be able to change, go ahead and let me know in the chat. Kind of think about all the different ingredients that we use, the different measurements that we used. What is something that we could change about this to test it again and see if there is a difference? Ooh, yeah, I'm seeing some people telling me in the chat they were thinking what would happen if I used a different size bag? Totally. So we were using kind of this medium size bag here. If we changed to a smaller bag or a bigger bag, that could be super interesting. Someone was saying earlier, what if I don't have this white vinegar, right? What if I only had apple cider vinegar or red wine vinegar? Well, that could be one of those variables that you change up, keeping everything else the same and see what happens. Another really easy one to change is your measurements, right? So instead of doing a half a cup, what if you only did a quarter cup? What if you did a whole cup? So I want you to be thinking about some of those things that you could change. Try your experiment again and take note in maybe a science notebook or a piece of paper and see what differences you notice happening. Ooh, awesome. I see some scientists saying they tried it with apple cider vinegar and it worked. Very cool. All right, my friends. Well, that is all that I have for you today, but I do have a closing challenge for you all. Now that you know those 4 signs of a chemical reaction, I want you to be on the lookout in your everyday life. Can you find more examples of heat, light, gas, and color change? I think you might be surprised at just how many chemical reactions are happening all around us. Thanks, scientists.
And huge thanks to you, Holly. We have, as you saw, chat was flowing. Thanks to everybody out there for participating in the experiment, for getting those pictures with the elephant toothpaste up on Instagram, and for asking some amazing questions. So we're going to get you a few questions here. A lot of the comments and questions, we're going by pretty quickly, were about your own safety. I like that people were a little bit worried when you mentioned, like, hey, there might be a loud noise. Is she going to be okay with that bag expanding with gas or with, the flames and all those kind of things? Keep your questions coming in, everyone. We've got time for at least a couple of them here. One big one, I think, was sort of related to your safety. People wanted to know what happened to those flames back when we were using, some of the salts that we may see in fireworks. Flames happened really quickly and then went away almost as quickly as they happened. What happened to the rest of that, that chemical reaction? Was the air hot? Did we have to be nervous about anything, ash dropping down? Can you tell us more about why does that reaction happen so quickly? And why was it so safe to just let flames go off into the air?
Yeah, well, thanks so much for bringing up that safety. It is always super important. And as we all promised at the beginning, we, of course, don't want to just be playing around with things. We always want to make sure we're using those safety guidelines and always having an adult to help us out when needed. But as for those flames and where they went, well, a couple things. We know that to have combustion, right, we need fuel, heat, and oxygen. So as soon as one of those 3 things runs out and is no longer here, it's going to stop the reaction. We're not going to have that fire anymore. So when I did 1 spray of our fuel, right, that fuel combined with the heat and the oxygen, we got that super cool reaction. But as soon as it burned up all that fuel, it had no more fuel to burn. So I knew that we had a really limited fuel supply, and that was going to end our combustion, which is why it's safe to make sure we're not going to get a runaway fire here. But yeah, it's also happening. Those little molecules that we were talking about, while they're getting burned up, those are transforming. They're changing into oftentimes things like carbon dioxide or water, which are pretty harmless to us in those small amounts.
Awesome. I'm glad it was safe, and it's also amazing we had the triangle right next to you to point out what we had lost in that reaction. So well prepared for the answer. Hey, another one is someone asked, hey, if humans are full of chemicals, or we're made of chemicals, and there's reactions going on all the time in us, why don't we give off light?
Oh, that would be so cool. I just had this picture in my mind of humans glowing everywhere. That would be super awesome. Yeah, well, it kind of depends. You know how we saw some of our different reactions, and some of them give off light, some of them give off heat, some of them give off gas, some do a combination of things. So again, it all comes down to those really small molecules that we were mentioning. So depending on what those molecules are and which ones they're interacting with, they just have different patterns and different signs that they release. But the thing that they all do have in common is energy. So really that, light and that heat, those are just forms of energy that are being released. It just changes depending on what those molecules are made out of.
Excellent. Thank you. Yeah, I love the idea of us glowing in the dark. So maybe we can change our chemistry somehow. But for now, we'll be happy giving off heat and honoring the answer that you gave us. One important one. Someone asked that I gotta make sure we get this across before they turn it into an experiment. Someone mentioned, is it safe to with the experiment we just did with the Ziploc bag? Is it safe to touch it, to taste it? I'm not sure. We want to make sure we get that warning out there. What are there any warning signs we need to know about what we're allowed to do with our reaction as we put on our scientist hat and want to figure out what just happened?
For sure. Yeah. Thank you so much for asking those follow-up questions. So I definitely picked a reaction that I knew was super safe for us all to do together today. So yes, it is safe to touch. You'll notice that I was not wearing, my safety goggles or my glasses anymore because I felt pretty confident this would be pretty safe for all of you all to do at home without that. I never recommend tasting any of your science experiments. So I would probably advise against that. However, as you know, right, baking soda and vinegar are often ingredients that we do use in edible products, right? Some of you might have used baking soda before when you're making a cake or making cookies. So some of those things are edible, but in general, I would recommend never tasting them when you're actually doing your science experiments. But that's definitely something you could follow up with an adult in your life that's hopefully helping you out with these.
All right. Thank you for that. Thank you for asking the question. Yeah, I think a good rule of thumb in the lab is look, have goggles if you don't know, but try not to taste the experiments until someone else has done that test for you to make sure that it's safe. Hey, thanks so much, Holly. Really appreciate all the insight here. Hopefully everyone got some great results and you guys know how to turn your demonstration into an experiment by changing up some of those variables and seeing what we get. As promised, we're going to put up those instructions here for how to participate in the social media contest. If you didn't get the picture you loved with the elephant, I almost said elephant ice cream, elephant toothpaste, then you have the option if you want to just post your results of your experiment. We'd love to see that as well, particularly if you do some of the follow-ups of changing up some of those variables. So as promised, we're going to put those up right now so that you guys know what those instructions are to be able to participate. Remember, one of the prizes is a spot in Curious World STEM Club. We actually have some members of the Curious World Club right here. You guys, I know, are going to do some bonus Q&A and experiments here with Pacific Science Center. So you guys, please hang tight if you're part of Curious World Club, and we'll do the after party here in just a second in the room you guys are in. For everyone else, there's information on your screen for how to join. And of course, you can also try to win by entering the contest. Thanks to all of you. Thanks again, everyone at Pacific Science Center, and we'll see everybody back here soon.